Hello everyone, today we are going to be learning about the characteristic equation and using eigenvalues to encode scalar equations of a specific matrix. So just as a review, let's quickly find the eigenvalues of a simple 2x2 matrix. I'll take an example where our matrix A is going to be equal to 2, 3, 3 minus 6. So once again, as a reminder, the eigenvalues are going to be the values lambda, where ax is equal to lambda x, where we have a matrix that transforms a vector x such that the output, aka the mapping, is scaled by a scalar quantity lambda. So this is the eigenvalue. And as a reminder, these eigenvalues are not universal to every single matrix, and these eigenvectors are not universal to every single matrix. A matrix has a specific subset or a basis of eigenvectors and corresponding eigenvalues, and all of this forms a subspace for this scenario for each individual matrix. So, of course, we have to be able to find this. How can we do that? We first begin by using the invertible matrix theorem, ax minus lambda x. I'm going to quickly rederive the equation that we originally used, which we can set as ix is equal to 0, a minus lambda I x is equal to 0. So if we take a minus lambda I, we get 2 minus lambda, 3, 3 minus 6 minus lambda. This matrix times a vector x is equal to 0. And if we want to find the scenarios where it's equal to 0, well, we have to remember the property by the invertible matrix theorem. This matrix has to be not invertible. To allow for non-trivial solutions. So in order to find non-trivial solutions, one easy way of checking whether a matrix is not invertible is by finding its determinant. And if its determinant is equal to 0, it's not invertible. So why don't we just take the determinant of this? So instead of solving for this, we can just take det a minus lambda I is equal to 0. And then we can find specific eigenvalues corresponding to it. So just quickly calculate the det of this. We're going to get 2 minus lambda times minus 6 minus lambda, all times subtracted by 3 times 3. So we get lambda squared from these two plus 6 lambda minus 2 lambda, so that's plus 4 lambda. And then this is minus 9, minus 12, this is going to be minus 21. Let's quickly factor. This is going to be equal to lambda minus 3 times lambda plus 7. So if determinant of this is equal to 0, then the two lambda values that satisfy this are lambda is equal to 3 and lambda is equal to negative 7. So that means that the eigenvalues of A are 3 and negative 7. We can box this. This is our final answer. Because with these values, if we put this back into this expression, this matrix, it's going to be, lambda is equal to 3. Let's just quickly plug this in. It's going to be 2 minus 3 minus 1, 3, 3, and minus 6 minus 3 is equal to minus 9. The determinant of this is equal to 9 minus 9 is equal to 0, meaning that this is not invertible, meaning that there has to be some non-trivial solution to a minus lambda I x is equal to 0. And we can solve for that, but in this example, we don't need to. And the same happens with lambda is equal to negative 7. 2 minus negative 7 is 9, 3, 3, minus 6 minus negative 7 is equal to 1. You can see where this is headed. 9 minus 9 is equal to 0 again, satisfying this. All right, so let's move on to another example. We'll talk about the characteristic equation with this. So this expression that we found over here, oh, I forgot to mention that this has to be equal to 0. It's a mistake, but for here, this has to be equal to 0 to satisfy 0. Obviously, it's the same work again. So this equation is called the characteristic equation. So the characteristic equation is also this actually. This is the determinant of the matrix minus lambda I is equal to 0. The polynomial that you get, the polynomial equation, is the characteristic equation, and it defines the eigenvalues of that specific matrix. Let's try with the larger matrix. This might look a bit daunting, but nevertheless, I think it's a good example to quickly find the characteristic equation. 5, 0, 0, 0, minus 2, 3, 0, 0, 6, minus 8, 5, 0, and negative 1, 0, 4, 1. Before we find the characteristic equation together, there is something interesting about this matrix that is going to help us quite a lot, and I would like for us to think about it, because obviously we don't want to find the determinant of a 4 by 4. It is going to take a bit, so I'm going to pause and let's think. Okay, so one thing we immediately notice is that, interestingly, this is a upper triangular matrix. Let's go ahead and find the determinant of A minus lambda I and see what we get. So determinant is of, I'm going to write out our main diagonal first. 3 minus lambda, 5 minus lambda, 1 minus lambda, and then negative 2, 6, 8, negative 8, sorry, negative 1, 0, 4, and the rest of these are 0, 0, 0, 0, 0, 0. Cool. So now the determinant of this. Now here's where the upper triangular matrix makes this extremely easy, because if a matrix is upper triangular or lower triangular, then that means that the determinant is just the product of the main diagonal. Meaning that this, if we set it equal to 0, we're going to get 5 minus lambda times 3 minus lambda, and I think you can see where I'm headed with this. 5 minus lambda, 1 minus lambda is equal to 0. Wow, that makes it really easy, because now, in this case, first note that there is 5 minus lambda squared times 3 minus lambda times 1 minus lambda is equal to 0. Our eigenvalues are going to be lambda is equal to 5, 3, and 1. 5 appears twice. So, and our characteristic equation, which is what we're actually trying to find here, is just this. We can expand it out, but this form makes it easier to understand it, and it's easier. Also, one important thing to keep in mind is if you want to verify that these lambda values are indeed eigenvalues of A, well, you can just row reduce A minus lambda I. So if I go back to this A minus lambda I for this one, because it's a 2 by 2, if I just row reduce this, I'm just going to draw a line over here. Well, over here you can see, you can just multiply 3 times row A plus, 3 times row A plus row 2, or row 1 and row 2, sorry about that. You're just, and then I'm also going to negate this, even though we're not supposed to do it in the same step, might as well. And also I forgot to add this here, but over right here, we can see that if you get a pivot in every single column, then something is wrong, because it's not an eigenvalue, because it shouldn't have a pivot in every single column. Over here we see that there's at least one column without a pivot column 2 in this case, and that's a good way of checking whether the eigenvalues that we've gotten are reasonable and they make sense. Okay. So another example, sometimes you're just given directly what the the characteristic equation is. Sorry, this is example 3, and we have to find the eigenvalues and also multiplicity. So with this example, actually with the previous example, I'm going to talk about algebraic multiplicity. So over here, we noticed one interesting thing. The eigenvalue 5 occurred twice in the characteristic equation. That is the algebraic multiplicity. It's the multiplicity as a root of the characteristic equation. It's the same concept as in algebra and pre-calculus and the other previous courses. So in this case, the algebraic multiplicity of the eigenvalues equal to 5 is 2. For 3 and 1, it is 1. And that's pretty important to know because in later units we're going to be talking about the geometric multiplicity and comparing it with the algebraic multiplicity, and there's a whole lot of stuff involved over there. So with this example number 3, we're going to find the algebraic multiplicity of the characteristic equation of in this case, a 6 by 6 polynomial, lambda to the 6th minus 4 lambda to the 5th minus 12 lambda to the 4th. Is equal to 0. It's just a easy factoring job, so minus 4 lambda minus 12 is equal to 0. Lambda to the 4th times lambda to this minus 6, lambda plus 2 is equal to 0. That means our 3 eigenvalues are going to be lambda is equal to 0, lambda is equal to 6, and lambda is equal to negative 2. From here, we can quickly find that the multiplicities are just 4, 1, and 1. What's interesting is that the multiplicities also tell you the dimension of the square matrix. The sum of them, of the algebraic multiplicities, is equal to the dimension n by n. So n, in this case, is equal to 6. Over here in the previous example, the multiplicity was 5, 5, 3, 1. So the multiplicity was 2, 1, and 1. That means that the sum was 4, and indeed we did have a 4 by 4 polynomial. In the first example, the two values we had were 3 and negative 7 with multiplicities of 1 and 1, and the sum of that was 2, which is, of course, a 2 by 2 polynomial. That checks out as well. So that is an introduction to the characteristic equation and algebraic multiplicity, and this is very useful in finding the eigenvalues and also the eigenvectors of the corresponding eigenvalues of different matrices. Hopefully with like tricks like you noticing that this is a triangular matrix and quickly just checking whether an eigenvalue makes sense makes it easier to ensure accuracy in finding eigenvalues and eigenvectors. So thank you.